The end of the lab is to find the mass of the black hole in the two-body system and analyze curve motion of the star. And part 2, we'll have to simulate the motion of the spaceship around the planet and the moon. To do that, we need to calculate gravitational force on spaceships and moon. In this lab, the fundamental physics principle is Newton's second law, which states that a body remains at rest or in motion at a constant speed in a straight line unless it is acted upon by a force. So in formula, it can expressed by F net equals m times acceleration, and also can express by F net equals m times delta v divided by delta t. So it's used to calculate perpendicular and parallel force of the curve motion in part 1, and it also used to get the velocity and position update formula in part 2. So in part 1, we have to find the mass of the black hole. So in order to do that, we find the delta momentum of the star, which is the average net force, and we kind of split the momentum into two directions in p hat and n hat, and we'll calculate the mass by using F net equals gravitational force caused by the black hole. So this is the video. So we can see there are a large number of the black hole mass, and we have to get the mean of the mass, which is 1.56889 times 10 the 44 power kg. And also in part 2, we'll have to simulate the motion of spaceship and the moon. The first step, we'll have to calculate the delta R between planet, moon, spaceship, and we calculate forces on spaceship due to planet and moon, and we kind of can predict the moon and spaceship velocity and displacement using update formulas. The next step is to get the initial velocity of the spaceship in order to have a figure orbit. So we first try with moon speed as the base, which I think will be faster if we try this. And we try with different strategies. For example, we set the sheet speed in negative axis and y and speed of y in positive y axis. For example, to let the velocity to be top left direction, or let the velocity to be bottom left directions. So you can't be in the right directions because you have to point inward, which is point to the black hole direction. And then I eventually try with negative 0.66x and also 1.5633y. So this is the video of the orbit. We can see that the orbit is a little bit strange because eventually, unfortunately, I can't find the exact number that would cause the 8-figure orbit. But I think it's the most closest one I ever tried. So reflection, part 1. The setting of the delta t makes a huge difference. So we'll often set to 1, which is closest to the reality of the mass of the black hole, which is 10 44 power. And also the net force is calculated by Newton's second law. So what we get is average net force during the time interval, not every moment of the net force. So this will cause some inaccuracy and need for a mean number. In part 2, we can see that the orbit is look like this. So we can see that the spaceship is almost there, but it just passed by the moon, not just by the moon by its gravitational force. So the next step what we do is to adjust a little bit of x or y coefficient to let the moon bind the spaceship. So discussion here. So I would say there are two different concepts. Net force is measured and vary in every moment, which is stands for a real interaction that is happening. But rate of change of momentum is measured in a time span. So it measures how momentum changes during the span. But the relationship between them is by Newton's second law. They're just equal in magnitude and directions. but two different concepts. So according to the diagram, these stars form a force chain, which black hole controls the star controls the planet controls the moon. So black hole is definitely the dominant interactions, and they will contribute more or less equally according to their order in the chain.